Yo, what's up, everyone? Welcome back. Sorry, let me adjust my camera. Um, Here we are, week 7, quarter 3, and we're doing another week of. I cannot figure out how to get this straight. It's like, yeah, perfect. Okay, cool. So, we have another week of graphing exponents this week. This is what we did last week, and it's all super similar to what we were doing with geometric sequences. But what we're going to do this week that sounds a little scary, I know to some students, but shouldn't be too bad, is we're going to start tackling some word problems again. And the last real big set of word problems we did in this class was the piecewise functions. And just so you know, I already told you guys, but this was the first year I taught that. And a lot of students thought that was difficult. Maybe that wasn't the best thing to do in like the third week of school or whatever it was, because it was intimidating. But the word problems we do for this unit are going to be not only kind of interesting, but really, really simple. Okay. This is the exponential form. And there's only two numbers involved always, right? And we already know this is going to be like the beginning of the equation, and this is like the common ratio. So we're going to tackle word problems. Today's word problem is going to be really simple. And then the next one, problem set 2, it'll be a little trickier, but not too bad. And then we are going to take a quiz at the end of this week as well. So that's where we're headed. I think we're crushing it. I mean, a lot of this stuff I've never even taught Algebra 2 before. I feel like we're doing really well with content, and I'm enjoying teaching. So hopefully, I mean, we're still getting a lot of views. So I'm really proud of you guys for fighting along, right? Like, it was not guaranteed. So anyway, this first question, I could even just say review problem 1, because this is exactly the kind of stuff that we did last lesson. It says, look at the following exponential equation, and we want to graph it by filling out the table. And a lot of times, as I've said, a table is the key to any kind of graph. And knowing what x values to put in is usually a good place to start. And if this is my sequence, remember that if you take any number and raise it to the 0 power, so 3 to the 0 power would be 1, okay? So that means that this, when x equals 0, is always going to be 1 times whatever this number is. So because this number was 1, if we plug in 0 into the equation, we get 1, okay? So if you're remembering the geometric sequences, this was considered the first term, and that's the same, but instead of the first term being 1 for an actual equation, it's going to be 0, okay? So maybe I didn't say that perfectly. This is review. But we're going to plug in 0, 1, 2, 3, and 4. For now, anytime we're doing these graphs, we're just going to plug in the first few positive numbers. And if we want to find the y, this kind of table is so much easier than plugging in every single point. You can plug in 1, you can plug in 2, you can plug in 3. That would work. But just remember that this is the common ratio. So let me write this. 1 equals when x equals 0, and 3 equals common ratio. Equations are all about knowing what the given information is. The common ratio is what you're multiplying every number to get to the next number. So in this case, the common ratio is 3, which means the number is tripling. So it's really easy. 3 times 3 times 3 times 3 times 3. That was one that I can do with my head, but I'm going to do a lot of these on the calculator, right? Just multiply down. Good. So again, this common ratio is 3. And compared to the other ones today, this is a really big common ratio. And anytime this number is greater than 1, the number is going to fly up. Okay, so you start at 1, and then it doesn't take very long to get all the way to 81. So that's our first one. And the graphing portion, we know that we have some negative, some positive examples. All the word problems we're going to do are going to be positive. So I'm cool with the one-axis graph, the one quadrant graph. And on the bottom here, I'm just going to go 0 to 4. And we know exponential. It's a pretty easy shape. What you should notice is this is easier than like a quadratic where we have to worry about the vertex and all that crap. So we're going from 0 to 100 because 100 is like a nice round number above 81. So I'm going to go up by fives, 5, 10, 15, 20, 25, every 5 times, like that. So I've made my scale, and now I just have to sketch. If the numbers aren't exactly on here, you really can just eyeball it. I'm not going to like look that hard. The first point is 0, so you always are going to start here, comma 1. And if every box is 5, that means we're like only 1/5 up that first box. Then it's 3, so a little over halfway to that first box. It always starts gradual and then flies. So 2, 9, 3, 27. Still gradual, but then eventually it's going to make a real break up to 81. I feel like we maybe even did this exact question before. I don't know. Anyway, that's what it looks like. Not the best drawing, but all I want you to take away from this is that the numbers go up a good amount because this common ratio is 3. So really, a lot of what we've been doing is figure out what does the graph look like depending on what the common ratio is. If we put something like half, remember from last lesson, the graph actually goes down. And our final thing that's going to be really useful now for the word problems is one of these common ratios that's in between 1 and 2, which sounds really, really funky, I know. Good. Okay. So to just look at the following exponential equation, and we want to graph it by filling out the table. For all of these, this is still really useful. I'm just going to do 0 and the first few integers. And no matter what these numbers are, they do the same thing to your equation always, where whatever is connected to x is the common ratio. And whatever is on the outside is the first number. So what we're trying to figure out here is what is this going to look like if this common ratio is 1.1. So first, let's just look at the number 100. This is a very, very quick kind of side note. I'll even zoom into my calculator here. This is our first number in this sequence, right? The first number is 100. And if this common ratio is any integer, like 2, 3, 4, 5, think that you're multiplying that to 100. And that's going to like double or triple. It's going to make this number way bigger. What we did last week was what happens if we multiply this to a fraction, right? What happens if the common ratio is 1/2? If you have anything that is like half or any fraction less than 1, we know that we multiply that to 100 and it's going to go down, okay? And that's the same thing as a decimal, right? So 0.2 is the same thing as 1/5. You multiply that to 100 and the number goes down. So if this number is less than 1, the number is going to go down. If it's greater than 2, like if it's 2, 3, 4, 5, this number is like exponentially rising, like doubling, tripling, etc. But if we have a number like 1.1, let's see what happens when we multiply that to 100. We get 110, which is actually like reasonable if you think about it compared to something like 2 or 3. The change is gradual, but it's still going up, okay? So if you want an exponential that's going to go more gradually, this number gets smaller and smaller, but it doesn't go lower than 1, right? If it went lower than 1, it's going to go down. But anything in between 1 and 2 is going to gradually go up. And the application here is money. We've already done sequences with this kind of common ratio. But all I want you to see is that because this is greater than 1, but only a little bit greater than 1, this number is going to gradually go up. So let me zoom out, and it'll make more sense in the next question. but that's our little setup. We have 100, and we're going to multiply it to 100. Sorry, multiply it to 1.1 a few times. So 110, 121, 133. So that's what it looks like. So let's just sketch this. Everything is in the positive quadrant, and the scaling itself is actually not so hard here, right? All of my numbers are in between 100 and 161, compared to something that the range is kind of a lot bigger. So here, I'm still going to start at 0, but I think I'm going to go from 0 to 200. And we're going to see how the shape of this is. That's the big goal. If I'm looking at this, this doesn't really look to me like it's exponential, right? I think exponential in my head, and I think the number is getting way bigger. But let's see if this is actually going to match that shape. So I'm going to go 0, go by tens, 10, 20, 30, 40, 50. We start at 100. The next number is 110. The next number is 121. So this is going to go up 1 and a little bit more for my next box. Then it's 133. So it's actually all playing out around here. So might as well just kind of label that more. And if I go a little too quick over the graphing part, I am sorry. That's something you could talk to me about, or slow yourself down and go back. But this is the scale that really matters for this one. 100, 110, 121, and then it's going to go to 133. And then 146. And then 161. So if we're looking at this, this looks almost more linear. Sorry, let me use this. This is better. It almost looks linear, right? It almost looks like it's going straight up and not going exponential. But what I want you to notice is that the distance is getting a little bit bigger as we move along. So all exponential means is that your number is slowly but surely increasing its slope, or how much it's rising from point to point. Here we went from 1 to 3, and then 3 to 9, and then 9 to 27. Every gap is bigger. And here, every gap is slightly bigger, but still bigger. 100 to 110 is 10 points. 110 to 121 is 11. So it's only one bigger, but the increase is increasing. So if I were to guess, like, it looks kind of linear now, but it might eventually start moving up. Good. Let's do our final example, which looks daunting, but it shouldn't be. And this is our first word problem before we do a bunch of word problems next time. It says, imagine the bank gives you a loan of $12,000 with an interest rate of 5% per year. So this is just like the word problems we did with geometric sequences. But what I want you to think now is you want to graph them. And usually if you were to do this kind of math in the real world, you would use an equation and not a sequence. First, it just says identify the initial amount and the common ratio. So think here that the bank is giving you $12,000. And what an interest rate means is that every year that you don't pay the bank back, you have to pay 5% more than was in the bank the year before. Okay? And what can be a little confusing about that is that you have to pay interest on the amount from the year before, not on 12,000. So first, what I mean by that is we know the initial amount is 12,000, and the common ratio here is 0.05, or the interest rate is 0.05. And we want to write an equation for how much money you'll have in X years. So the equations have been given today, but don't forget that if we're looking at this last one, I was just setting us up to do a money example. This number in an equation is the starting amount. Before we started, when we were at 0, we had 100, y equals 100. So the initial amount here is 12,000. Whatever your starting value is goes on the outside. The inside is the common ratio or the interest rate. But here's the important part to realize. The interest rate is 0.05, but the common ratio is 1.05. And the logic to that is that if 12,000 is the amount of money they give you, the interest there is $600. You owe them $600 more, but you still have to give back the initial amount, right? So in the second year, you're going to have to give them back not only $12,000, but $600 more. So instead of doing that kind of math, instead of multiplying 12,000 by 0.05, think that it's this money plus itself. So if you multiply this by 1.05, I hope I'm saying this well. This represents multiplying it by itself and the interest, and you get the same value. Okay? So I think that's really fascinating. I'm really happy we're learning about this. But this is the equation. Whatever the interest rate is, you put here. Whatever the initial loan amount is, you put here. And this is how loans are calculated. There's a harder formula depending on some stuff that we won't do, like how much you compound and stuff. But if you're interested, it's really cool. And this is kind of the basis. How much money will you owe in 10 years? Before we do that, I'm just going to fill, I know this is a long table, but we're only doing one of these. Let's just talk about what happened. This is that first year. At the beginning, you start with this much money. And what we just figured out is that if you keep the loan for 1 year, this is how much money you would owe, right? So you needed the money, but you got it back and you got a little bit more. This is how much you'd have to give them after the first year. But you could think, oh, I'm just going to keep adding 600, right? The interest amount. The reason that this formula works so well is that after this is like the amount of money we have, you're going to pay interest on the entire thing the next year. So instead of paying 600 in interest, you now have to pay 630 plus this initial amount. So if you just keep multiplying the value by 1.05, it's going to tell you how much you would owe after every year. And we're just going to keep going down. But the gist is that this number is going to start increasing by more and more. The number is going to get really big after a few years. If you don't pay off your initial interest, it's going to compound and it's going to become an issue really quickly. Okay, so let me just put a few of these in. I'll even fast forward the video. Okay, so in this case, if you didn't pay the loan back, it looks like after 10 years, you might owe as much as $20,000, which doesn't sound awful, but our interest rate here wasn't that high. I've been watching The Sopranos, and like if they were to do interest, they'd probably make it like 20% every single week or something ridiculous, right? So you really get screwed over. But here the interest rate isn't that high, but even after 10 years, like you have to pay $8,000 more, right? And that's kind of the idea of exponential. This number rises by more and more the farther we go because your interest is compounding. Where if you waited now 20 years, it'd be something like $30,000 that you owe. Okay, so this is still exponential. Eventually, this is going to become millions. Like we can just keep clicking this, and you owed $12,000, but in 30 years you owe $50,000. And that's what exponential increase means. So I think that's really, really cool. Good. Let's just graph it. I'm going to fast forward the graph because I think we've covered everything. I think it was a great lesson. Good. So I scaled up to 20,000 because this is approaching 20,000. But everything's going to happen really above here. We started with 12,000 and it's going to go up gradually to start. Okay. So here, honestly, that graph does not look good. It looks pretty linear to me, and that's fine. I'm not going to really press it. But as we were seeing, as we move to the future, this 12,000 become much, much more. So you'll have a few of these questions to do on your own. I think we crushed it. For this one, how much money would you owe in 10 years? You could multiply down, and that's totally fine. But I just want to show you, if you wanted to find any year, you just have to plug that into the equation. So on my calculator, I would do 1.05 to the 10th, multiply that to 1200, and we see the exact same answer. So that's that. One more lesson next time related to this, and then we'll take a quiz. Really proud of you. Woo.